Question 3 excuse me, of the 2010 Mechanics paper, Level 2 Physics. The high jump. Lucy is competing in a high jump event. She runs up to the bar, jumps over it, and lands on the mat, as you do if you're doing what you're intending to do. If you don't make it over, then anyway. A. She starts her run up by accelerating from rest. Note that, from rest. That means it's at 0 meters per second. At so she's accelerating at 2.21 meters per second squared for 2 seconds. Calculate the distance she travels in this time. Write the answer to the correct number of significant figures. So the process for a mathematical question like this, or a good process, is to write down everything that you know, or you can note it in the variables above. I'm going to write it down in the space below. So we've got the initial velocity, which was rest, 0 meters per second. We've got the acceleration, 2.21 meters per second squared. Velocity, you should really write the units for velocity even if it's 0. And the amount of time it takes is 2.0 seconds, two significant figures. Note all the significant figures because the next question is going to ask you about that, especially since this one asks you to calculate to the correct number of significant figures. And we're after the distance that she travels in this time, so that's our question mark, the one we're trying to find out. So what's something that links all of these variables together? An equation, a kinematic equation, since she's accelerating. And the most obvious one that stands out would be excuse me, d equals vi times t plus a half at squared, because this one uses all of them, all of those variables, and we can conveniently get rid, since she's starting from rest, we can conveniently take that one away because vi is 0. 0 times the time will be 0, so 0 plus half at squared is still half at squared. Okay, so the distance travelled in that time is going to be half times 2.21 times by 2.0 squared, and that gives our final answer is 4.4 meters, if I'm reading it correctly off the marking schedule. Not going to do the calculations, it takes too long. How many significant figures? Yes, that is to two significant figures. Unrounded, it's 4.42, but you can't round it to two significant figures because your limiting factor, the weakest link in the chain, is the data that you use in the calculation that has the least number of significant figures. In this case it's the time, which only has two significant figures. And that's kind of dealt with this question. Explain why I've used this number of significant figures. Because when you're multiplying or dividing, use least FF significant figures, which is 2SF 4 times. Okay, moving on. C. Use physics principles to explain why it is better for Lucy to land on the padded mat than it is to land on grass. Okay, so first thing to do is identify the difference between a padded mat and grass. So a padded mat is going to compress quite a lot when you land on it. Grass might bend and fall over, but that's not going to compress very much. So there's a couple of things there's actually 3 different ways that we could explain this. I've only really thought of 2 myself, but the marking schedule gives 3 possible ways to explain it. One is that it's a matter of impulse, so that as your total momentum is going to be the same when you hit the mat or when you hit the grass, but when you, and I'm not going to write this down in specific detail, I'm just going to explain the principles and then you can work out how you would have written it down from what I say. So the momentum is going to be the same as Lucy hits the grass or the mat. What we need to do though is to decrease the force, because the force is the one which is going to, the greater the instantaneous force, the greater the instantaneous damage, okay, if you like, the greater the damage. So to decrease the force we need to increase the time, and on the mat it does that. So the mat increases the time because it takes longer to compress the mat compared to bending over the grass, and in reality the grass is going to do very little and you're just going to hit the dirt, and the dirt will take a much shorter amount of time and therefore a much greater force to make your momentum decrease to 0. So that's one way to look at it. The other way is to look at work. Work is force times distance, because remember we're looking at force here. Anything that relates to force in this situation is going to help. So when we're considering work, both the mat and the grass will do work on you or on Lucy to slow her down. The mat, you would presume, is thicker, so it would take a longer, so that distance here is going to be greater for the mat, which will mean the force will be lower for the same amount of work, because the same amount of work has to be done in both cases. She'll have the same kinetic energy, which has to be reduced to zero by dissipating that energy to heat and sound and whatever. To convert energy, you need to apply force over a particular distance. So anyway, that explains why for the grass, the distance is going to be much smaller, so the force will be much larger for the same work. Okay, and the other way to look at it is acceleration. Because acceleration is proportional to force, the acceleration being the change in velocity over change in time, you'll have the velocity is going to be the same, roughly the same anyway, when she hits the mat compared to when she hits the grass. So for the same velocity, maybe we should rearrange this so that the change in velocity is equal to the acceleration times the change in time. So for the same velocity, we want to decrease the acceleration so that we're also decreasing the force from that proportionality relationship. So to do that, to decrease the acceleration and the force, we have to increase the time, and you get that same increase in time with the compression of the mat, which takes longer to compress than it does for the grass. Okay, so that's all the three different ways you can do it. This consideration of change of momentum, impulse, is the probably the best way and the one that we most expect, because, yeah, just as by tradition perhaps.